What is going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, I have got three different capacitors. Can you see them all? There's three of them. Let's see. Three different capacitors. I have got one that is like massive, one that is medium-sized, and one that is basically the size of like the back of an expo marker, right? Like it's pretty tiny. Now, they also have different heights to them. So if you look, there's different heights, right? This one is far larger, okay? All different sizes. However, I'm going to share one interesting thing with you. On each of these, they are rated at 1 farad. 1 farad, 1 farad, 1 farad of capacitance. There it is, 1 farad. They're all 1 farad. So that confuses me because I was under the impression that capacitors are devices that have an ability to store charge. And if the capacitance is a measurement of how much charge something can store, then shouldn't something bigger have more capacitance? And how in the world does this itty-bitty little guy have the same capacitance as this guy right here, which looks much, much, much larger? So that's my question to you all today is how do we figure this out? What can change? Clearly there are physical properties that are changing with these capacitors in terms of shape and size, but apparently they still have the same capacitance. So that's kind of the question I'm thinking about today. How can I get the same capacitance on different shaped sizes things if the idea behind a capacitor is that it stores charges? And this one looks like there's more room to store charges on. So let's discuss it, okay? So we went back to the same simulation we did our previous lab on, and we graphed something. We said, let's look. We basically took our capacitor now, and we manipulated it. We had some sliders. We said, hey, we can adjust the size of the plate this way, and we can adjust the separation. So we called this one the area. We had a slider for area. We said we can grab this and we can adjust the slider, make the plate bigger or smaller. We can go ahead and adjust this slider and make them further away or closer together. Let's first talk about the area thing because I'm curious about that. We're not going to take actual data. So instead what we're going to do is we're going to look at how charge is stored is impacted by the area, right? If I go ahead and slide this thing around, what happens to my charge? Well, if I go ahead and make this larger, if I make the plate physically larger, it makes sense that as the area increases, the amount of charge stored on it is bigger. It's like saying if I get a bigger classroom, I can put more kids in it. If I have a bigger restaurant, I can fit more tables in it, right? This just should make good sense. Given that we do not change the voltage of the battery, the power supply, if I make these plates larger, I should be able to have more room to put more charge on. And the simulation absolutely agrees with that. So if I have zero area or no plate at all, there should be no charge stored on it. As I increase the area, I see an increase in charge, which means there's a direct relationship. Charge on a plate is directly related to the area, assuming we have no change in potential difference across the battery. That's the first thing we found out. Okay, that doesn't help me explain this though, because like this guy is small, this guy is big. This guy can store a lot more charge than this guy at the same voltage, which is key, because if they can store more charge at the same voltage, they should have different capacitance. But they don't. They have the same. So there must be more to this story. So we start playing around again, and we say, okay, well, I wonder what happens when I separate these things further or closer. Let's keep everything else the same. Let's keep the area the exact same. Let's not change the area now. Let's simply change this. Now, if I don't change the area, I'm not changing the charge on each plate. If I don't change the charge on each plate, well, then the electric field that exists between these two plates also doesn't change. Hear me out. If the electric field, remember our equation for parallel plates, if our electric field doesn't change, but I decrease the distance between those two, the potential between them goes down, which is interesting, right? If I increase the distance across this, the potential would go, what did I say, decrease or increase? If I make the plates closer, distance goes down. voltage goes down or potential difference goes down. If I increase the distance across those plates and the E field stays the same, the potential gets larger. You can store more charge if those two plates are further away because they can handle a larger potential difference. It's physically different. Let's think about that. If I bring these plates closer together, that lowers the distance. It lowers my potential difference, which means it's going to increase my capacitance because voltage, potential difference, is inversely related to capacitance. That's wild. And vice versa. If I separate them, I pull them much further apart. If I pull them really far apart, that really increases my potential difference. That actually drops my capacitance. So hang on now. Let's look at this. If I'm looking at this and I want to graph distance, how is distance related to voltage? Well, as distance goes up, potential difference goes up as well. We would say potential difference is related to distance. All of this is to say, when I relate it back to capacitance, which is key, capacitance and area have a direct relationship. If you make the plate larger, it can store more charge, capacitance goes up. However, capacitance and distance, just like voltage, have an inverse relationship. As you increase the distance, the capacitance goes down. We end up with a couple of proportionality statements. Capacitance is directly related to plate area. Capacitance is inversely related to the plate distance. And what we come up with is the beginnings of an equation, a second equation, when capacitance is equal to some vacuum permittivity constant times area over distance. And this is true as long as we're not changing more than one variable with it. So if I want to find the capacitance of something, I would look at the area and the distance. Wait a second. There's a relationship between area and distance. This plate has a very large area, but also is separated by a very large distance. This capacitor has a teeny tiny little area to store charge, and it's also separated by a pretty itty bitty distance. And this is like the Goldilocks zone. It's like a pretty average size plate, and then they're separated by an average distance. So to answer the previous question, how in the world can we have different size capacitors which store charge? They have different sizes to store charge. How can they possibly have the same capacitance? Well, if they have a larger plate, they must have a different distance, in this case a larger distance, so that way a little teeny tiny plate has a little teeny tiny separation. This will have the same capacitance as something like this. So this is the answer to our question about that. And then there's one more quality to a capacitor we didn't exactly talk about. For now, we've kind of ignored the fact that parallel plate capacitors have insulating material between them, and based on that material actually dictates their capacitance. This is more of a relational thing. But if I want to actually find the capacitance of something, I need to know the I'm drawing a blank on I need to know the permittivity constant. No, permittivity constant? No, the dielectric constant. Every material has a dielectric. It tells you like the insulating quality of that material. So this equation over here is great if the insulating material stored between the capacitors to prevent charge from flowing. It's this space here. Whatever occupies this space between the capacitors, that insulating material has a dielectric constant to it. So I need to know how insulating that material is. If it's air, that constant is 1, and we don't need to worry about it. If it's something else like glass or Teflon or plastic, it's going to have a different dielectric constant, and so we have to take that into account when considering this. So if you go to your equation sheet does not say, epsilon times A over D equals capacitance. Instead, I believe it says, I think it's written in this order, it's K, which is your dielectric constant for the material, times that permittivity constant, times A over D. That is how you can calculate the capacitance of a capacitor based on its physical qualities, not based on what you're measuring as we did in the first lab. So, can you have different size capacitors with the same capacitance? Yeah! Just change their area, their separation, or the material they're made out of. If you got questions, you drop it in the comments, you ask me in class, you send me an email. All right, till next time. See ya!